Hello there, and welcome to our channel, where quiet curiosity meets the deep end of science and wonder is allowed to take its time. Tonight, we're not going to talk about how the universe began or where it's heading. Instead, we're going to look under our own feet and ask something a little unsettling, something simple but not easy. What if we're not the first thinkers, builders, explorers? What if long before pyramids and satellites and bedtime science channels, another civilization lived here on Earth, rose to something complex and then vanished? I don't mean mythical lost continents or alien tourists. I mean an actual civilization, something homegrown, biological, intelligent, perhaps in ways we don't fully understand. Something that lived and died so long ago the planet may have forgotten it completely. If that sounds like the setup to a science fiction story, well, it sort of is. But it's also a serious scientific question, one that's been quietly bouncing around geology labs and cosmology conferences for years. The idea isn't that we'll find skyscrapers under Antarctica or smartphones embedded in coal seams. It's more subtle than that. The question is, if there had been an advanced civilization millions of years ago, could we even tell? Would the traces survive the slow, relentless grinding of the Earth's geology? Or would everything, cities, tools, language, even bones, have been recycled back into rock and soil, indistinguishable from nature? This is the kind of question that doesn't demand an answer so much as an adjustment in perspective. It invites us to consider time not on a human scale, but on a planetary one, where mountains rise and fall like waves and oceans open and close like eyelids. In that kind of time, what does it mean to be permanent? What does it mean to leave a mark? We tend to think of our own civilization as the peak of a long, steady climb from simple life to complex thought, a straight line pointing ever upward. But what if history isn't a line? What if it's a cycle, a series of pulses of complexity that rise, flourish, and then fade back into the deep background rhythm of the planet? The thought is both humbling and strangely comforting. It suggests that intelligence might not be a one-time accident, but a recurring possibility, a pattern the universe might try again and again. So, settle in, maybe lie back if you can, and let your thoughts slow down to the pace of plate tectonics. We're going to take a long look backward, not through human history, but through the crust and silence and heat of deep time itself. Because before we can ask whether someone came before us, we have to understand just how much time we're dealing with and how good this planet is at wiping the slate clean. Before we drift too far into the deep past, let's establish how we're going to explore this. This isn't a search for proof in the way a detective might look for a culprit. We're not here to argue for or against any particular theory. Instead, we're going to hold the question itself up to the light and see what it reflects. Our method is simple: curiosity without conclusion. We will treat this as a thought experiment, a way to test the limits of what we know and what we can know. We'll look at the evidence that geology, chemistry, and biology provide, but we'll also look at the gaps in that evidence. Because sometimes the most interesting stories are found not in what's there, but in what's missing. We'll start by defining what we even mean by civilization. The word is loaded with assumptions, often tied to images of cities, writing, and technology. But we need a broader definition, one that could include forms of intelligence and organization we might not immediately recognize. Could a civilization exist without metal, without monuments, without leaving a single fossil? From there, we'll journey into the Earth's own memory system, the geological record. We'll explore how the planet writes its history in layers of rock, sediment, and ice. We'll see how forces like erosion, tectonic subduction, and time itself act as relentless editors, erasing most of what happens on the surface. Understanding what gets wiped away is just as important as understanding what survives. Then we'll turn to the signals that might endure, not buildings or bones, but more subtle traces, chemical anomalies, unusual isotope ratios, synthetic molecules, or disruptions in ancient ecosystems. This is the heart of the Silurian hypothesis, a formal scientific paper that asked how we might detect a pre-human industrial civilization. We'll walk through its logic, not to find a lost city, but to learn how to think like a planetary archaeologist, sifting through deep time for the chemical fingerprints of intelligence. We will also touch upon the stories humans have told for millennia, myths of worlds before our own, of great floods that wiped the slate clean, of knowledge lost to time. These aren't scientific data, of course, but they are a form of record, a cultural memory that sometimes hints at real events, even if distorted by ages of telling. We'll treat them not as proof, but as echoes, faint signals from a past we can no longer see directly. And finally, we will turn the question back on ourselves. What traces are we leaving right now? If our own civilization were to vanish, what would a geologist find 50 million years from now? By understanding our own geological legacy, we can get a better sense of what to look for in the layers beneath us. This approach requires patience and a comfort with uncertainty. We are not aiming for a final verdict. The goal is not to convince you that an ancient civilization existed, nor is it to prove that it didn't. The goal is to explore the possibility in a way that opens up a deeper appreciation for the planet we live on, the vastness of its history, and the fragility of our own place within it. We're here to wonder, to question, and to listen to the silence between the layers of rock and time. It's in that silence that the most profound possibilities often reside. So let's proceed, not as advocates, but as observers, with our minds open and our assumptions held lightly. The journey is the destination here, and the questions are more important than the answers. Right now, wherever you are, you're sitting on or very near the surface of a planet. It's not just a rock floating through space. It's wet and windy and full of movement. It erupts and heals, freezes and thaws, decays and blooms. It makes weather. It supports life. In fact, it doesn't just support life, it creates the conditions for it. And it's been doing this for billions of years without ever seeming to need a manual. Before we get carried away, let's take a breath. Feel the weight of your body, the gentle, constant pull of gravity holding you in place. That force is not just local. It's the same force that holds the moon in orbit and the Earth in its path around the sun. It's a connection that runs from the center of your own mass to the center of the galaxy. Now think about the air you're breathing. It's a mix of nitrogen, oxygen, argon, and a few other trace gases. But that mix isn't an accident. It's the product of billions of years of biological activity, of ancient forests and oceanic plankton breathing out the very oxygen your lungs are now pulling in. The air in your room has a history. It has been cycled through volcanoes, absorbed by oceans, and passed through the cells of countless organisms before it found its way to you in this moment. Look around your room. The furniture, the walls, the light from your phone or screen, all of it ultimately comes from the earth, the wood, the metal, the electricity, the air you're breathing as you listen to this. Everything in your life has passed through Earth's hands, so to speak. It's easy to forget that because we've built so many layers between ourselves and the raw material of the planet. We live in apartments and cities surrounded by plastics and networks and things we plug in and charge. But take away all of that and we're still living inside the skin of a very old, very active, very complex system. And it's a system that doesn't sit still. Deep beneath your feet, even if you can't feel it, the ground is slowly shifting. Tectonic plates float on molten rock. Oceans rise and fall, not just with tides, but with long, slow pulses of temperature and salinity. The atmosphere breathes in carbon and breathes out storms. Clouds build, rain falls, rivers swell, aquifers refill, and somewhere on the other side of the world, a rainforest drinks deeply without asking permission. These aren't random events, they're part of cycles, massive, interconnected, self-balancing cycles that somehow keep going without anyone at the wheel. Or so it seems. By grounding ourselves here, in this physical moment, we can begin to appreciate the scale we are dealing with. Our own lives unfold in seconds, days, and years. The planet operates in millennia, epochs, and eons. To ask a question about its deep past, we have to first feel its present, to recognize that we are not separate from it. We are a part of it, made from the same materials, governed by the same forces, breathing the same air. So why does this question matter? Why spend time wondering about a civilization that may or may not have existed millions of years ago? It matters because it forces us to confront the scale of time and our own place within it. We tend to see human history as the main event, the central story of this planet. But geologically speaking, all of our recorded history, from the first cuneiform tablet to the device you're listening on now, fits into a layer of sediment so thin it might not even be visible in a future rock core. Our entire existence is a geological whisper. To consider a previous civilization is to entertain the idea that there might have been other whispers, other moments of complexity that rose and then were reabsorbed by the planet's immense, slow-moving systems. This thought does something important. It decentralizes us. It suggests that intelligence, technology, and culture might not be a one-time phenomenon, a final destination for evolution. Instead, they could be a temporary state that a planet can pass through more than once. This has implications for how we think about our own future. If a technologically advanced civilization could vanish so completely that we can't even be sure it was here, then what does that say about our own permanence? Our cities of steel and glass, our global networks of information, our satellites in orbit. We see them as enduring monuments to our success, but the planet sees them as temporary arrangements of minerals that will, given time, be weathered, buried, and recycled. This perspective isn't meant to be nihilistic. It's meant to be humbling. It encourages a long-term view, one that looks beyond immediate political or economic cycles and considers the geological consequences of our actions. The chemical changes we are making to the atmosphere and oceans today are being written into the rock record. These will be our most lasting fossils. They will persist long after our buildings have turned to dust and our languages have been forgotten. The question of a prior civilization also has profound implications for the search for life elsewhere in the universe. We often assume that if we find signs of intelligent life on another planet, it will be a living civilization, one we can communicate with. But it's statistically more likely that if we find any evidence of extraterrestrial intelligence, it will be the ruins or chemical traces of a civilization that has long since gone extinct. By learning to search for the faint signals of a lost civilization on our own planet, we are practicing the very techniques we might need to find one on another world. We are learning to read the language of planetary memory, a language written in isotopes, sediment layers, and atmospheric chemistry. In this sense, the Earth itself becomes a laboratory for astrobiology. It's the only example we have of a planet that has sustained life for billions of years, and it may hold clues about the life cycle of civilizations themselves. Do they all inevitably face resource depletion or climate change? Do they all leave similar chemical fingerprints? Or are there other paths, other ways of existing that leave a lighter touch? Ultimately, asking, what if we're not the first, is a way of asking, what are we? Are we a geological accident, a brief spark of complexity in an otherwise indifferent universe? Or are we part of a deeper, recurring pattern? We don't have the answer, but the act of asking changes how we see the world. It invites a sense of wonder, a respect for the deep past, and a more sober understanding of our own fragile present. As we move forward, we'll keep a few key threads in mind, threads we will return to as we explore the different layers of this question. First, there is the thread of erasure. We will look closely at the geological and biological processes that actively dismantle and hide evidence over deep time. This isn't just about things fading away. It's about an active system of recycling that is fundamental to how Earth works. Understanding this process is key to knowing what we can realistically expect to find. Second, we will follow the thread of the signal. If a civilization did exist, what kinds of traces would be the most stubborn, the most resistant to erasure? We will investigate the concept of geochemical fingerprints, the subtle but potentially widespread changes in the planet's chemistry that might be the last surviving echo of an industrial or technological society. This is where we will lean on the formal science of the Silurian hypothesis. Finally, there is the thread of recognition. Even if a signal survived, would we know what we were looking at? This thread explores the limits of our own perception and scientific frameworks. It asks whether we might have already encountered anomalies in the geological record without realizing their potential significance, simply because they don't fit our expectations of what a civilization's remains should look like. These three threads, erasure, signal, and recognition, will guide our journey. We'll pick them up and put them down as we move through different kinds of evidence, from the tangible chemistry of rock layers to the more ethereal echoes in human myth. Think of them as the different instruments in a quiet orchestra, each playing its part in a larger composition about time, memory, and the search for a story that may be older than our own. Before we go looking for lost civilizations, we should probably decide what we're even looking for. What exactly is a civilization? And what would make one count, scientifically speaking? In everyday conversation, we tend to think of civilization as a kind of upgraded version of society. Cities, writing, governments, maybe a skyline. But that's a very narrow, very modern view. Even in human history, civilizations have looked wildly different. Some built vast cities with monuments and roads. Others left almost nothing behind but language and land use, and yet we'd still call them civilizations. In archaeology and anthropology, the definition gets a bit more careful. Civilizations are usually identified by a set of traits: urban centers, specialized labor, centralized authority or governance, surplus agriculture, organized religion, social stratification, the development of writing or symbolic communication, and long-distance trade. Those are the big ones. But not all civilizations tick all the boxes, and some do it in ways we might not expect. So when we talk about the possibility of a forgotten or deeply ancient civilization, we need to broaden our thinking. We're not necessarily looking for giant pyramids or computer chips. We're looking for evidence of complexity, social, technological, or ecological things that don't happen by accident. Things that suggest a group of beings organized themselves at scale over time for purposes that went beyond immediate survival. It's helpful to think about civilization less as a finish line and more as a spectrum. Somewhere between isolated tool use and planetary engineering, there's a lot of room. A culture that developed complex systems for managing its environment, that stored and transmitted knowledge across generations, or that created large-scale coordinated structures, even if those structures were biodegradable, could qualify. The key is evidence of collective, intentional action that has a lasting impact. What's crucial for our question is that this impact would need to be detectable after millions of years. This shifts the focus from cultural traits like writing or religion to physical ones. Specifically, a civilization advanced enough to leave a geological trace would likely need to be energy-intensive. Any society that manipulates its environment on a global scale, whether through agriculture, construction, or industry, consumes vast amounts of energy. That energy use, especially if it involves burning fossil fuels, altering landscapes, or synthesizing new materials, is what leaves the kind of chemical fingerprints we might still be able to find today. So, for our purposes, let's define a geologically detectable civilization as a species that harnessed external energy sources to a degree that it significantly altered planetary systems like the carbon cycle, the nitrogen cycle, or the composition of sediments. This could be an industrial civilization like our own, but it doesn't have to be. It could be a biologically based civilization that mastered genetic engineering and created massive, energy-capturing ecosystems. Or it could be something we can't even imagine. The point is not what it looked like, but what it did to the planet's chemistry. This definition has an important advantage. It's not species-specific. we're not just looking for intelligent primates. The civilization could have been reptilian, insectoid, aquatic, or even fungal. As long as it harnessed energy and altered its environment at a planetary scale, it fits our criteria. This frees us from our own biological biases and allows us to look for the signal of activity, not the fossils of a particular life form. This is a very different way of thinking about civilization. It's not about monuments or empires. It's about metabolism, planetary metabolism. And that is a signal that, however faint, might just be stubborn enough to survive. When we talk about ancient history, we usually mean a few thousand years. The pharaohs of Egypt, the builders of Stonehenge, the earliest known scripts etched into clay tablets. Even when we reach back to the dawn of human civilization, we're still only going back about 10 or 12,000 years. That's a blink in geological time. It's closer to now than to almost anything else that's ever happened on this planet. And yet to us, it already feels like the deep past, already enough to fill libraries with mystery, debate, and speculation. But the Earth is old, staggeringly old, not just millions of years old, billions, about 4.5 billion years, give or take a few hundred million. For the vast majority of that time, there were no humans. There weren't even mammals for most of it. And for much of it, there was no life on land at all. Life spent a lot of time swimming or waiting or evolving in microscopic obscurity. And yet, despite how empty that sounds, this was when most of Earth's story was written, layer by layer, rock by rock, in forms that speak slowly and forget quickly. Let's place ourselves on this timeline. Complex animal life, the kind with bodies and skeletons, only appears around 540 million years ago, during an event called the Cambrian explosion. Before that, for about 3 billion years, life was almost entirely microbial. This vast, quiet period is when the fundamental chemistry of the planet was being shaped. The first land plants appeared around 470 million years ago. Dinosaurs roamed from about 230 million to 66 million years ago. The first mammals were small creatures, scurrying in the shadows of the dinosaurs. And our own genus, Homo, appeared only about 2.5 million years ago. Modern humans, Homo sapiens, have only been around for about 300,000 years, and civilization, as we typically define it, is a phenomenon of just the last 10,000 years. This timeline is important because it tells us where to look and where not to. If a complex, technologically capable civilization existed, it would have to have arisen after the Cambrian explosion, when the biological building blocks for large, intelligent organisms were in place. That still leaves a window of over 500 million years, an immense stretch of time full of different geological eras, different climates, and different arrangements of continents. During this time, the planet's surface was completely reworked multiple times. The supercontinent Pangea formed and broke apart. Ice ages came and went. Sea levels rose and fell by hundreds of meters. The very ground we're standing on may have once been at the bottom of an ocean or the peak of a mountain range that no longer exists. This is the context we must hold in mind. We are not looking for a lost city in a jungle. We are looking for the ghost of a civilization on a planet that has repeatedly erased its own surface. The geological record is not a pristine library. It is a collection of burned books, torn pages, and fragments of sentences, with most of the volumes missing entirely. When you start looking closely at the shapes that life takes, the way trees branch, shells curl, petals align, or crystals form, you start to see patterns, not just resemblance, but repetition. Certain structures show up again and again across different scales and environments. Some are symmetrical, some are spiral, some fit ratios that can be described with simple numbers. And while all of these forms can be explained by physical processes, the consistency is hard to ignore. Symmetry is probably the easiest one to spot. It shows up in faces, bodies, leaves, insects, snowflakes. When both sides of something mirror each other, whether vertically, horizontally, or rotationally, we call it symmetrical. That kind of balance can be structural, helping an organism move more efficiently or distribute weight evenly. But symmetry also seems to appeal to perception. Human brains are wired to recognize it quickly. We tend to find symmetrical faces more attractive. We use symmetry in design, architecture, and symbols. It registers as orderly, familiar, complete. In nature, symmetry often serves a purpose. A butterfly's wings match because they form together. A starfish has radial symmetry that helps it move and respond to its environment. Leaves grow in matched pairs to capture light evenly. Even many viruses are built with symmetrical protein shells, not because they need to be beautiful, but because symmetry is efficient. It allows for repeated use of the same genetic instructions. From a material standpoint, it's a shortcut. Make one piece, then copy it over and over. But not everything is mirrored. Some of the most interesting structures in nature are spiral. You see spirals in snail shells, hurricanes, whirlpools, and galaxies. You see them in pine cones and sunflower heads, in fingerprints and animal horns. Spirals often appear where growth is involved. They allow structures to expand outward while staying compact. As the organism adds material, a new scale, a new layer, a new petal, the spiral makes room without disrupting the whole. Many of these spirals follow a mathematical pattern called the Fibonacci sequence. It's a series of numbers where each new number is the sum of the two before it, 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence shows up in how petals are arranged, how tree branches split, how seeds are packed. The ratio between Fibonacci numbers approaches what's known as the golden ratio, a proportion that seems to recur in both nature and art. It's not universal, but it's common enough that it invites attention. These patterns don't require any intelligence to appear. They can emerge naturally through processes of growth and competition. For example, if a plant is growing new leaves and trying to minimize how much each one blocks the sunlight for the others, it may evolve a spiral arrangement. That arrangement, in turn, aligns with the golden angle, a fraction of a full rotation that distributes elements efficiently. No one designed it to be beautiful. It just works, and yet it ends up being beautiful anyway. That sense of emergent order, of patterns that look designed but arise from simple rules, is a theme we'll see again and again. It complicates the search for intelligence because nature itself is structured in ways that can mimic intention. This is not a flaw in the idea, it's a boundary condition. It means that to argue for an artificial origin of a pattern, the pattern must be significantly different from what we know nature can produce on its own. A perfect right angle in a rock formation is interesting. A million perfect right angles forming a grid is another matter entirely. This is where scale and repetition become important. A single anomaly can be dismissed as a coincidence. A widespread, repeated anomaly requires a better explanation. If we were to find, for instance, a layer of sediment from 60 million years ago that contained perfectly spherical microscopic beads of a specific metallic alloy distributed globally, that would be difficult to explain with known natural processes like volcanism or meteor impacts. It wouldn't prove the existence of a civilization, but it would create a compelling mystery that demanded investigation. The challenge is that most of the time, nature's patterns and artificial patterns overlap. Humans build with circles, spirals, and hexagons because those shapes are structurally efficient, the same reason they appear in nature. A road follows the path of least resistance, just like a river. A city's network can resemble the mycelial network of a fungus. This is called convergent evolution, where different systems independently arrive at similar solutions to similar problems. This convergence is what makes recognition so difficult. Are we seeing a signal of past intelligence, or are we just seeing a different expression of the same underlying physical and mathematical principles that shape our own world? Distinguishing between the two requires more than just finding a pattern. It requires understanding the context in which that pattern formed. Was it created in an environment that would naturally produce such a shape? Or does it stand in stark contrast to everything around it? The search for a lost civilization, then, is not just a hunt for artifacts. It is a search for things that are out of place, out of time, or out of balance with their environment. It is a search for a signal that is loud enough and strange enough to be heard above the constant, beautiful, and structured noise of the natural world. Now let's look at the Earth as a whole system. From a distance, our planet doesn't look like a machine or a program. It looks like a living thing. Not in a literal biological sense, but in the way it regulates itself, maintains balance, and responds to change. It behaves like a single, integrated system, where the oceans, atmosphere, land, and life are all constantly interacting, influencing one another in a vast, self-sustaining feedback loop. In the 1970s, a scientist named James Lovelock proposed a name for this idea, the Gaia hypothesis. He suggested that the Earth's biosphere and its physical components, the air, water, and rock, are so closely integrated that they form a complex, self-regulating system that maintains the conditions for life. The idea wasn't that the Earth is a conscious being, but that its systems work together in a way that creates a kind of planetary homeostasis. If the planet gets too hot, certain biological and chemical processes work to cool it down. If too much carbon dioxide builds up in the atmosphere, the oceans and forests absorb it. It's as if the Earth has a kind of planetary immune system, not one with cells and antibodies, but one with feedback loops and chemical cycles. For example, marine algae produce a chemical that helps form clouds over the ocean. These clouds reflect sunlight, which helps to cool the planet's surface. This is a simple feedback loop. Warmer oceans lead to more algae, which leads to more clouds, which leads to cooler temperatures, which then reduces the algae population. The system naturally seeks a balance. We see similar feedbacks everywhere. Forests create their own rainfall through transpiration. The weathering of rocks, a process influenced by microbes, pulls carbon out of the atmosphere over millions of years, acting as a long-term thermostat. The balance of oxygen and carbon dioxide in the air is actively maintained by the breathing of plants and animals. These aren't isolated mechanisms. They are interconnected, woven into a planetary web where a change in one place can ripple through the entire system. This concept of a self-regulating Earth is crucial to our question. If a past civilization existed and became energy-intensive, it would have had to interact with these Gaian systems. It would have either learned to work within them or it would have disrupted them. If it disrupted them, we might be able to see the scar of that disruption in the geological record. Imagine an ancient civilization that burned fossil fuels on a massive scale. This would release huge amounts of carbon dioxide, just as we are doing today. The planet's systems would try to compensate. The oceans would absorb more carbon, becoming more acidic. The climate would warm, leading to changes in weather patterns and sea levels. These changes would leave behind chemical and geological traces, a spike in carbon isotopes, a layer of sediment showing signs of ocean acidification, fossil records indicating a rapid shift in climate. We might find evidence of a fever in the Earth's past, a sudden, anomalous warming event that doesn't fit with known natural cycles like volcanic activity or orbital shifts. This disruption would be the signal. It wouldn't tell us who was there or what they were like, but it would tell us that something pushed the planetary system out of balance in a way that resembles what an industrial civilization does. Conversely, a civilization might have learned to integrate itself into the planetary system. It might have developed technologies that were sustainable, cyclical, and non-disruptive. Such a civilization would be much harder to detect. Its legacy wouldn't be a scar, but a subtle enhancement of the existing natural systems. Perhaps they engineered ecosystems to be more productive or resilient. Perhaps they developed forms of energy that left no chemical trace. In this case, the evidence of their existence would be almost invisible, a kind of deep harmony rather than a jarring disruption. We would be looking not for a mistake, but for a moment of unusual stability or complexity in the geological record. Either way, thinking of Earth as a responsive, self-regulating system gives us a new way to search. We are no longer just looking for objects. We are looking for the planetary scale consequences of action. We are listening for a moment when the slow, steady heartbeat of the Gaian system either skipped a beat or found a new, more complex rhythm. Before we go any further, I'd love to know where in the world you're listening from tonight, and what time is it right now where you are. Funny, isn't it? The topic is ancient civilizations, and yet here we are, separated by seconds and miles, quietly sharing this same little moment. No matter where or when you are, I'm glad you're here. If this kind of slow burn question is your kind of question, I'd be thankful if you tapped like or subscribed. It helps this sleepy little signal reach other curious minds. No pressure, of course, just an invitation like the faint trail of footprints that might, if we look closely, lead somewhere unexpected. So, how would we distinguish the impact of a lost civilization from a natural event? This is the central challenge. The Earth has its own history of dramatic change. There have been periods of intense volcanic activity, massive methane releases from the ocean floor, and asteroid impacts, all of which can cause rapid climate change, mass extinctions, and leave behind strange chemical signatures in the rock. The Paleocene-Eocene thermal maximum, or PETM, which occurred about 56 million years ago, is a perfect example. During the PETM, global temperatures soared by 5 to 8 degrees Celsius in just a few thousand years. The oceans became highly acidic, and there was a major extinction event in marine ecosystems. The cause is thought to be a massive release of carbon into the atmosphere, but the exact source is still debated. It could have been volcanic activity, the melting of methane hydrates, or something else entirely. What's striking about the PETM is that the geochemical signature it left behind, a sharp negative spike in carbon-13 isotopes, looks remarkably similar to the signature we are creating today by burning fossil fuels. So, if we were to find another PETM-like event in the geological record, how could we tell if it was caused by natural processes or by a forgotten industrial civilization? The conventional scientific view, and the one we must respect as the default, is that these events are natural. The Earth is a dynamic planet, and its history is filled with episodes of extreme change. There is no need to invoke a lost civilization to explain events like the PETM when known geological mechanisms are sufficient. The principle of Occam's razor applies here. The simplest explanation is usually the best. A massive volcanic eruption or a destabilization of ocean sediments are simpler explanations than the rise and fall of a completely unknown technological species. Furthermore, for a civilization to be the cause, its impact would have to be not just large, but also rapid and global. While the PETM was geologically fast, it still unfolded over thousands of years. Our current human-induced changes are happening over centuries, an order of magnitude faster. A truly industrial signal might be identifiable by its unprecedented speed. We would need to find a chemical shift in the rock record that is sharper and more abrupt than anything that can be explained by natural processes. However, there is an alternative way to look at this. While a single event like the PETM can be explained naturally, what if we found a cluster of anomalies that all occurred at the same time? For example, what if a sharp carbon isotope spike coincided with a layer of unusual synthetic-like molecules, a spike in heavy metal concentrations like lead and cadmium, and a mass extinction event that selectively affected large animals? A single one of these signals could be natural. All of them happening together in the same thin layer of sediment would be much harder to explain. It would look less like a natural catastrophe and more like the ecological footprint of an industrial society. The problem is that our ability to resolve time in the deep past is limited. A layer of sediment that represents a few thousand years might appear as a single, sharp line in a rock core. Distinguishing between an event that took 200 years and one that took 2,000 years can be impossible when looking back 100 million years. The data gets blurred. Another challenge is the baseline. To identify an anomaly, we need to know what's normal. For many parts of Earth's history, our understanding of the normal climate and chemistry is incomplete. The geological record is full of gaps. We might see a strange signal and not realize it's strange because we don't have a clear picture of what came before or after, so we are left in a state of careful ambiguity. The mainstream view holds that there is currently no evidence in the geological record that requires a pre-human civilization to explain it. Natural processes seem sufficient to account for the anomalies we've observed, but proponents of the thought experiment would argue that we haven't looked in the right way. We have not been explicitly searching for clusters of industrial-like signals. Our scientific instruments and models have been designed to find natural causes, so that is what they find. This isn't a conspiracy, it's just the nature of scientific inquiry. You tend to find what you're looking for. Until we begin to actively search for techno-signatures in the geological record, we can't definitively say they aren't there. We can only say they haven't been found yet. If you want to hide something forever, you don't need to bury it deep or burn it up. You just need to leave it on the surface of the Earth and wait. Not days or decades, but long enough for geology to do its work. Because the Earth is not still. It breathes, it shifts, it consumes, and almost everything built on top of it eventually disappears. We don't notice this much in everyday life. We tend to think of landscapes as permanent. Mountains seem eternal. Rivers always seem to be in the same place. Cities feel like they've always been where they are. But geologists see something else. They see motion in what looks solid. Over enough time, even the hardest rock flows, bends, or breaks. Even the tallest peaks crumble. The surface of the Earth is constantly being reworked. And that means anything resting on that surface is temporary by default. The two main forces of erasure are weathering and tectonics. Weathering is the slow breakdown of materials by wind, rain, ice, and chemical reactions. It turns mountains into sand, concrete into gravel, and metal into rust. Tectonics is the movement of the Earth's crustal plates. This process is even more powerful. It can raise new mountain ranges, open new oceans, and, most importantly, recycle the old crust. A process called subduction is particularly effective at erasing history. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced downward into the Earth's mantle, where it melts. Anything on that plate, sediments, fossils, or the ruins of a coastal city, is completely destroyed. The entire ocean floor is recycled this way every couple of 100 million years. This means that if a civilization existed more than 200 million years ago and was primarily based on coastlines or islands, its physical remains are likely gone forever, melted back into the planet. Continental crust lasts longer, but it is not immune to erasure. Erosion can strip away layers of rock that took millions of years to form. Glaciers can scrape landscapes clean down to the bedrock. Volcanic eruptions can bury entire regions under thick layers of ash and lava. So, what survives? The fossil record gives us some clues. For an organism to become a fossil, it needs to be buried rapidly in sediment, in an environment without much oxygen, where it can be protected from decay and scavengers. These conditions are rare. It is estimated that less than 1% of all species that have ever lived have been preserved as fossils. And even then, what we find is usually just hard parts, bones, teeth, shells. Soft tissues, and by extension most cultural artifacts made of wood, fiber, or leather, almost never survive. This is what's known as survivorship bias. The geological and fossil records are not a complete history of the past. They are a history of what was durable enough and lucky enough to be preserved. This bias makes finding evidence of a non-human civilization incredibly difficult. We would be looking for something that was not only intelligent but also happened to build with materials that could withstand millions of years of geological processing, and then left those durable artifacts in one of the few places on Earth where preservation is possible. The odds are not in our favor. It's tempting to think about this question in terms of language we're familiar with. We talk about the Earth remembering or forgetting, as if it's a conscious entity with a memory, but these are just metaphors, and it's important to be clear about their limits. The Earth does not have intentions. It does not decide what to keep and what to erase. It simply operates according to the laws of physics and chemistry. The processes of geology are indifferent. A rock layer containing the fossil of a dinosaur is no more or less important to the planet than a layer of volcanic ash or a seam of coal. When we say the Earth has a memory, what we really mean is that it has a physical record. This record is not written in a language of symbols, but in a language of matter, of minerals, isotopes, and structures. And like any language, it has its own grammar and vocabulary. A geologist can read this language. They can look at the grain size of a sandstone and infer the speed of an ancient river. They can analyze the chemical composition of a limestone and determine the temperature of an ancient ocean. They can study the magnetic orientation of particles in a basalt flow and know which way was north when the rock cooled. This language is powerful, but it is not narrative. It does not tell stories of individuals or societies. It tells stories of processes, of erosion, deposition, heating, cooling, and pressure. To find a civilization in this record, we would have to find a signal that looks like a process but cannot be explained by any known natural process. This is why anthropomorphic language, while useful for imagination, can be a trap. If we think of the Earth as hiding its secrets, we might be tempted to look for deliberate patterns or codes. But if we think of it as a physical system, we are more likely to look for disruptions, anomalies, and unexpected outputs. For example, instead of looking for a message in the rock, we might look for a sudden, inexplicable shift in the global carbon cycle. Instead of searching for ruins, we might search for a layer of sediment containing unusual concentrations of heavy metals or synthetic-like polymers. The Earth isn't speaking to us in words. If it is speaking at all, it's speaking through feedback. A change in one part of the system causes a response in another. These responses are the verbs of the geological language. And a civilization, especially an industrial one, would be a very powerful verb. It would not just exist within the system, it would act upon it, leaving a cascade of responses in its wake. Our task, then, is to learn to read those responses and to distinguish the ones caused by a geological subject from those that might have been caused by an intelligent one. Let's walk through a hypothetical scenario. Imagine you are a geologist in the distant future, or perhaps an alien visitor studying Earth's rock layers. You are drilling a core sample from what was once a deep ocean basin. As you analyze the layers, you move backward through time. You pass through the layers of the recent past, then into the Holocene, the Pleistocene, and deeper still. Then, at a depth corresponding to roughly 65 million years ago, you see the famous K-Page boundary, the thin layer of iridium-rich clay that marks the asteroid impact that wiped out the dinosaurs. But you keep drilling. You go deeper, past the Cretaceous, the Jurassic, the Triassic. Finally, you reach a layer from the late Carboniferous period, about 300 million years ago. And here you find something strange. In a thin, dark band of shale, you detect a number of anomalies all at once. First, there is a sharp, negative carbon isotope excursion, even more rapid than the one seen during the PETM. It suggests a massive, sudden release of light carbon into the atmosphere, consistent with the burning of vast quantities of fossil fuels. Second, alongside this carbon spike, you find microscopic spherical particles of fly ash and soot, the byproducts of coal combustion. Third, the layer contains elevated concentrations of heavy metals like lead, mercury, copper, and cadmium, arranged in ratios that are not typical of volcanic deposits. Fourth, you discover trace amounts of complex, persistent organic pollutants, molecules that resemble synthetic pesticides or industrial plastics, substances that should not exist in the Carboniferous period. And finally, analysis of microscopic fossils in the layers just above this anomaly shows a sudden mass extinction event, particularly among large land animals and certain marine species, while smaller, more adaptable organisms and deep-sea life seem less affected. What would you conclude? A single one of these findings could be dismissed, A carbon spike could be a methane release. Heavy metals could come from a peculiar type of volcanic eruption. But all of them together in one thin, globally distributed layer. That pattern does not fit any known natural phenomenon. The speed, the specific chemical cocktail, and the selective nature of the extinction all point to a single, coordinated cause, an energy-intensive global civilization that experienced a rapid expansion and then a sudden collapse. You would not have found their cities, you would not have their fossils, you would not know what they called themselves or what they believed, but you would have found their footprint. You would know they were here. This is the kind of evidence the Silurian hypothesis suggests we should be looking for. Not a needle in a haystack, but a strange discoloration of the entire haystack. Now let's shift the scale. Instead of drilling a single core, imagine we have a comprehensive map of the Earth's geology from 300 million years ago. We can see the shape of the supercontinent Pangea, the location of mountain ranges, and the flow of ancient rivers. In this context, we might find other, larger-scale clues. For example, we might notice unusual patterns of erosion. In certain regions, we might see evidence of widespread systematic deforestation leading to accelerated soil loss and altered river deltas downstream. In other areas, we might find vast, unnaturally geometric patterns of land use, visible only through satellite-based geological surveys. We might detect the faint remnants of large-scale mining operations, unusual geological voids, or vast deposits of mine tailings with a distinct chemical signature. Perhaps we would find evidence of river systems that were deliberately re-engineered, with ancient channels that defy natural topography. These would be macro-scale signals, evidence not just of chemical output but of physical landscape engineering. Such traces would be much harder to find and even harder to confirm. Erosion and tectonic activity would have heavily distorted any such features over 300 million years. A straight line might become a gentle curve, a rectangular pit might become an irregular depression. But with advanced imaging techniques like seismic tomography or gravity gradiometry, it might be possible to detect the ghostly outlines of such artificial structures buried deep within the crust. There is also the possibility of finding evidence in the fossil record, but not in the way we usually think. Instead of looking for the bones of the civilized species itself, we might look for the effects of their civilization on other species. For example, a sudden, widespread appearance of skeletal deformities in certain animal populations could be a sign of industrial pollution. The fossil record of pollen might show an abrupt replacement of diverse native flora with a small number of monoculture crops. The fossils of domesticated animals might show a rapid change in size, shape, and distribution, distinct from the slower pace of natural evolution. These would be indirect biological signals, the ecological echoes of a civilization's presence. Again, none of these signals alone would be conclusive, but taken together, chemical spikes, landscape modifications, and ecological disruptions, all dating to the same narrow window of time, they would build a powerful circumstantial case. We would be like archaeologists reconstructing a lost society not from its pottery and tools, but from its trash, its pollution, and the scars it left on the land. It would be a history written not by the victors, but by the planet's own patient chemical response. For something that hangs in the sky every night, the moon is a little strange. It's large compared to the planet it orbits. Its gravitational effect is strong enough to influence the oceans, and its role in Earth's stability is more than just a side effect. It might actually be one of the most important factors in why life has persisted here as long as it has. The presence of a large single moon is unusual for a rocky planet in our solar system. The leading theory for its formation is the giant impact hypothesis, which posits that a Mars-sized body collided with the early Earth, and the debris from this collision coalesced to form the moon. This event was chaotic and contingent. It didn't have to happen, but because it did, it set in motion a series of physical interactions that have profoundly shaped Earth's habitability. The most significant of these is the stabilization of Earth's axial tilt. The Earth's axis is tilted at about 23.5 degrees relative to its orbital plane, which is what gives us seasons. Without the Moon's gravitational influence, this tilt would be unstable. It could wobble chaotically over geological time, swinging from nearly 0 to more than 85 degrees. Such drastic shifts would lead to extreme and unpredictable climate change, with polar regions sometimes pointing directly at the sun and equatorial regions freezing over. It would be incredibly difficult for complex life to adapt to such a volatile environment. The Moon acts as a gravitational anchor, keeping the Earth's tilt stable within a narrow range. This has allowed for the development of relatively stable climate zones and predictable seasonal cycles over billions of years, providing the long-term environmental consistency that complex life seems to require. The Moon's gravity also drives the ocean tides. This constant mixing of coastal waters is thought to have played a crucial role in the origin of life by creating intertidal zones with repeating wet-dry cycles that could have concentrated the chemical building blocks of life. Tides also drive ocean currents, which help to distribute heat around the planet, further moderating the climate. Over time, tidal forces have also caused the Earth's rotation to slow down. In the early history of the Earth-Moon system, a day was only about 5 or 6 hours long. The Moon was much closer, and tides were enormous. The gradual slowing of the Earth's spin to our current 24-hour day has had a significant impact on climate and weather patterns. This intricate dance between the Earth and Moon, this system of coupled feedback, highlights a key theme in our exploration. Habitability is not a simple property of a planet, but an emergent feature of a complex system. A planet might be in the Goldilocks zone of its star, but without a stabilizing moon, the right kind of tectonic activity, or the right chemical balance, it may never become a suitable home for complex life. When we ask if a pre-human civilization could have existed, we are also implicitly asking if the Earth has been continuously habitable for intelligence for the past 500 million years. The Earth-Moon system suggests that at least one of the key conditions for long-term stability has been in place. The presence of the Moon is not proof of design or intention. The giant impact was likely a random event, but the consequences of that event were profound. It gave Earth a partner that helped to calm its climate, stir its oceans, and steady its spin. It's another example of how a contingent, accidental event can become a fundamental part of a planet's life support system. If a past civilization existed, it would have lived under the same moon we do, subject to the same tides, the same seasons, and the same long-term stability. The moon would have been a constant in their sky, just as it is in ours. And any record they left behind would have been written on a planet that was already old, stable, and deeply shaped by its relationship with its oversized, essential, and strangely beautiful companion. The Earth is not a perfect timekeeper, but it is a patient archivist. It records its history in layers of sediment, in the chemistry of ancient ice, and in the magnetic alignment of volcanic rocks. These archives are vast but incomplete, like a library with most of its books destroyed and the remaining pages scattered and torn. Yet from these fragments we can reconstruct the broad outlines of the planet's past. The most common type of archive is sedimentary rock. Layers of sand, mud, and organic matter accumulate over time in oceans, lakes, and riverbeds. As these layers are buried, they are compressed into rock, preserving a snapshot of the environment at the time of their formation. The thickness of a layer can tell us about the rate of sedimentation. The type of rock tells us about the environment. Sandstone forms in rivers or deserts, shale in quiet waters, and limestone from the shells of marine organisms. Within these layers, fossils provide direct evidence of past life, while chemical signatures like isotope ratios can reveal ancient temperatures and atmospheric conditions. Ice cores, drilled from the polar ice sheets of Greenland and Antarctica, provide a much higher resolution archive, but one that only goes back about 800,000 years. Each layer of ice represents a year's snowfall, and trapped within the ice are tiny bubbles of ancient air. By analyzing these bubbles, scientists can directly measure the composition of the atmosphere in the past, including the levels of greenhouse gases like carbon dioxide and methane. Dust and pollen trapped in the ice can tell us about past winds and vegetation. This is how we know with certainty that current CO2 levels are higher than they have been at any point in the last 800,000 years. Another archive is written in the Earth's magnetic field. The field is generated by the planet's liquid iron core, and it occasionally reverses its polarity. When volcanic rocks cool, magnetic minerals within them align with the field at that time, locking in a record of its orientation. By dating these rocks, geologists have built a timeline of magnetic reversals stretching back hundreds of millions of years. This magnetic barcode can be used to date rock layers and track the movement of continents. These archives provide the context for our search. If a civilization left a chemical fingerprint, it would have to be found within one of these records. A spike in carbon would appear in both sedimentary rocks and ice cores. A layer of synthetic pollutants would be preserved in lake sediments. A massive extinction event would be visible in the fossil record. The archives are where the signal would be stored, but these archives have limitations. As we've discussed, the geological record is full of gaps called unconformities, where layers have been erased by erosion. The older the record, the more gaps there are. The ocean floor is completely recycled every 200 million years, so any deep ocean sediments older than that are gone forever. The resolution of the record also decreases as we go further back in time. An ice core can resolve individual years, but a 100-million-year-old rock layer might represent a time span of thousands or even tens of thousands of years. This blurring effect makes it very difficult to detect events that were geologically brief, like the entire lifespan of an industrial civilization. This is the central paradox of our inquiry. The archives that could hold the evidence of a past civilization are the very same archives that are most likely to have been degraded or erased by time. The signal we are looking for is faint, and the medium in which it was recorded is noisy and incomplete. We are listening for a whisper in a geological hurricane. This doesn't mean the search is pointless, it just means we have to be realistic about what we can find. We are unlikely to find a clear, unambiguous artifact. We are much more likely to find a pattern of anomalies, a convergence of strange signals in a narrow slice of time that hints at something out of the ordinary. The archives may not give us a story, but they might give us a question. As we continue to sift through the planet's deep archives, we will keep our focus on the kinds of signals that could, in principle, survive. We've touched on the idea of chemical fingerprints and large-scale engineering, but we'll also need to consider the biological record. How might a civilization alter the course of evolution itself, and would such changes be distinguishable from natural processes? This is a more speculative thread, but it's one worth following because if intelligence is a powerful force, its effects might not be limited to chemistry and geology. They might be written into the code of life itself. We will return to this idea, to the possibility of a biological echo, after we have looked more closely at the conversations between life and the planet's other major systems. When people talk about forests as the lungs of the planet, they're usually referring to the fact that trees and plants absorb carbon dioxide and release oxygen through photosynthesis. That's true, of course, but it's only a small piece of what's really happening. Forests don't just produce oxygen, they influence weather. They regulate temperature. They affect rainfall patterns thousands of kilometers away. There are vast network systems that shape the chemistry and physics of the atmosphere, not just locally, but globally. Consider the Amazon rainforest. It's often described as a carbon sink, a place where carbon dioxide is absorbed and stored, helping to regulate the climate. But that's not the full story. The Amazon also generates its own rain. Trees there release water vapor through transpiration, contributing moisture to the air. This moisture forms clouds which produce rain which feeds the trees. It's a self-reinforcing loop, a kind of biological feedback system. And it doesn't just affect the Amazon basin. The water vapor from those forests drifts on air currents and influences weather across South America. Even rainfall patterns as far away as the United States and Africa can be affected by the health of the Amazon. This pattern isn't unique. Forests across the globe play similar roles. If forests are Earth's breath, then the oceans are its circulation, covering over 70% of the planet's surface. Oceans absorb heat, carbon, and oxygen, redistribute them, and send them back into the atmosphere in new forms. They store more carbon than the atmosphere and the land combined. They move vast amounts of energy from the equator toward the poles. They influence the formation of clouds, the paths of storms, the success of harvests. And like the forests, they don't operate randomly, they operate in cycles. Take the biological pump. This is the process by which the ocean pulls carbon dioxide from the atmosphere, converts it into organic matter through photosynthesis in microscopic plankton, and sends it down into the deep sea. When those organisms die, this carbon can remain buried for centuries. Without this pump, atmospheric carbon levels would be far higher. Plankton, so small we can't see them with the naked eye, perform nearly half of all photosynthesis on Earth. They are the base of the marine food web, and their health is directly tied to the health of the planet's climate system. The intricate conversation between biomes like forests and oceans and the atmosphere they inhabit demonstrates the planet's capacity for self-regulation. But it also reveals its vulnerabilities. These systems are resilient, but they have thresholds. If pushed too far, they don't just bend, they can break or flip into a new state. This is where the signature of a past civilization might be found. A sufficiently advanced civilization would have the power to alter these biome-atmosphere conversations on a global scale. Widespread deforestation, for example, would do more than just release carbon. It would disrupt the planet's hydrological cycle, potentially causing regional drying and desertification. The geological record of such an event might show a sudden shift in pollen fossils, a change in river sediment patterns, and a chemical signature of soil erosion, all happening in a geologically brief period. Similarly, polluting the oceans could disrupt the biological pump. If a civilization released toxins that harmed plankton populations, the ocean's ability to absorb carbon would decrease. This would lead to a rise in atmospheric CO2 and global warming. The signature in the rock would be a layer with a mass extinction of marine microorganisms, followed by geochemical evidence of ocean anoxia, a lack of oxygen, and a spike in global temperatures. These are not hypothetical scenarios. We have seen similar events in Earth's past, often linked to massive volcanic eruptions. The key to identifying an artificial cause would be the absence of a clear geological trigger. If we found a major biome collapse and a resulting climate shift in the rock record, but there was no evidence of a supervolcano or an asteroid impact at the same time, we would be forced to look for other explanations. Another possibility is that a civilization could have engaged in large-scale geoengineering, attempting to deliberately manage the planet's climate. Perhaps they seeded the oceans with iron to stimulate plankton growth and draw down carbon. Or perhaps they released aerosols into the stratosphere to reflect sunlight and cool the planet. Such projects would leave behind highly unusual and specific chemical traces, layers of sediment enriched with iron, or strange sulfur isotopes, for example. These would be smoking guns, clear evidence of technological intervention in the planet's climate system. The search for a lost civilization, then, can be framed as a search for a moment when the natural conversation between life and the planet was either catastrophically interrupted or deliberately hijacked. We are looking for a ghost in the planetary machine, a moment when the system behaved in a way that suggests the influence of a mind. Looking at the outer forms of life, it's easy to be impressed by how well everything seems to fit together. But when you go inside into the cell, the nucleus, the molecules that run everything, that sense of fit doesn't go away. If anything, it becomes sharper. At the core of all this is DNA, the molecule that stores genetic information. Every known living thing uses DNA or its close cousin, RNA, to carry the instructions for how to build and maintain itself. DNA isn't just a substance. It's a code. It's built from 4 types of molecules: adenine, thymine, cytosine, and guanine. arranged in sequences that determine how proteins are made. Those proteins, in turn, run the machinery of life. It's often compared to a language or a computer code, not just because it uses a limited alphabet, but because it has structure, syntax, and meaning. The way that information is read, copied, and interpreted is so organized that it feels less like a chemical reaction and more like a process. When you look at how DNA works, it's not just about storing information, it's about managing it. There are sequences that act like start and stop signs, signaling when a gene should be activated. There are regulatory genes that control other genes. There are repair systems that scan for errors during copying and correct them. All of this happens inside a structure just a few micrometers across in every cell. That level of organization is striking. The standard explanation is evolution by natural selection. Small changes in genetic material create variation, and the variations that improve survival get passed on. This process, over billions of years, has led to the incredible complexity we see today. But even within that framework, the system itself stands out. It's not just functional, it's robust, flexible, and information-rich. This has led some to wonder whether the genetic code itself shows signs of being more than just a frozen accident. The analogy between DNA and computer code is more than just a useful teaching tool. It may offer a way to think about potential biosignatures of intelligence. Our own civilization is just now beginning to develop the tools of genetic engineering, like CRISPR, which allow us to edit the code of life directly. We can insert new genes, delete old ones, and rewrite the instructions of an organism. In the future, it's conceivable that a civilization could engage in planetary-scale biological engineering, creating new species, designing novel ecosystems, or even encoding information into the genomes of organisms for long-term storage. If a past civilization had reached this level of biological mastery, could we detect it? The traces would be subtle, but perhaps not impossible to find. We might look for genes that appear suddenly in the fossil record with no clear evolutionary precursors. Or we could search for genetic sequences that show signs of non-natural patterns, perhaps a kind of mathematical regularity or an encoded message. This is highly speculative, of course. Distinguishing an artificially designed gene from a naturally evolved one would be incredibly difficult, especially after millions of years of subsequent evolution. However, there are some potential markers. For example, if we found a family of genes that used a different genetic code than the universal one shared by all other life on Earth, that would be a profound anomaly. Or if we discovered a piece of junk DNA that, when decoded, revealed a non-random pattern like the digits of pi or a sequence of prime numbers, it would be hard to dismiss as a coincidence. Another possibility lies in the fossil record of extinction and radiation. A civilization might have caused a mass extinction through engineered plagues or by introducing invasive, genetically modified species. Conversely, they might have triggered a burst of biodiversity by creating new life forms. Such an event would look like an unnatural evolutionary pulse in the fossil record, a sudden flowering of novelty that doesn't fit the typical pace of evolution. The resilience of biological information is also a factor. DNA is a remarkably stable molecule. Under the right conditions, in cold, dry, or anoxic environments, it can survive for hundreds of thousands, perhaps even millions of years. We have sequenced the genomes of Neanderthals and mammoths. It is not entirely out of the realm of possibility that fragments of ancient, engineered DNA could still exist, waiting to be found in permafrost or deep sediments. The search for a lost civilization, then, is not limited to geology and chemistry. It could also be a search through the living library of the genome itself. We would be looking for a single, anomalous verse in the epic poem of evolution, a line that suggests another author was at work. Before there was one great land mass, the Earth was a very different place. Hundreds of millions of years before Pangea came together, the planet was a patchwork of smaller continents scattered across the globe and drifting slowly over a deep, ancient ocean. These fragments of land did not stay in one place for long, at least not on geological timescales. They moved as they always do, carried on the slow conveyor belts of tectonic plates. As these fragments drew closer, oceans shrank between them. When land meets land, the collision is not gentle. Rocks crumple like paper under enormous pressure. Whole mountain ranges rise where two plates lock together. The Appalachian Mountains in North America and parts of the Atlas Mountains in Africa are relics of these ancient impacts, the scars of collisions that helped stitch Pangea together. By about 335 million years ago, this process of continental collision had culminated in the formation of Pangea, a single supercontinent that stretched from pole to pole. The existence of such a massive, unified landmass had a profound impact on the Earth's climate and the evolution of life. With nearly all the land gathered in one place, the interior of the continent was thousands of kilometers from the ocean. This created a harsh continental climate with extreme temperature swings between summer and winter, and vast deserts where moisture from the sea could not reach. The coastlines, by contrast, were subject to powerful monsoons. Life had to adapt to these new, extreme conditions. The formation of Pangea also facilitated the spread of land animals and plants across the globe. For the first time, organisms could migrate between what would later become separate continents without crossing oceans. This is why we find fossils of the same species, like the reptile Lystrosaurus, in South Africa, India, and Antarctica. They were not swimming across oceans, they were walking across a single, connected land. Pangea was not permanent. It began to break apart around 175 million years ago, a process that continues to this day as the continents drift toward their modern positions. The story of Pangea provides a perfect case study for the challenges of finding a lost civilization. The supercontinent existed from roughly 335 to 175 million years ago, a 160 million year window well within the time frame that complex life has existed on Earth. If a civilization arose during this period, it would have inhabited a world with a fundamentally different geography and climate than our own. Imagine a civilization that emerged in the vast interior desert of Pangea. It would have had to be incredibly adept at managing water and extreme temperatures. Its technology might have focused on subterranean living, moisture harvesting, or solar power. But its remains would be buried today under layers of sedimentary rock in places that are now temperate forests or farmlands scattered across different continents. Finding the connected ruins of such a civilization would require piecing together geological evidence from North America, Africa, and Europe, and recognizing that they were once part of a single, contiguous settlement. Alternatively, a civilization might have flourished along the monsoonal coastlines of Pangea. It would have been a maritime culture, perhaps, living in the shadow of the vast global ocean of Panthalassa. But as Pangea broke apart, its coastal regions were stretched, submerged, and transformed into the continental shelves of today's oceans. The remains of such a civilization would now lie deep underwater, buried under millions of years of sediment, and likely destroyed by the tectonic processes that formed the Atlantic Ocean. The very existence of supercontinents like Pangea underscores the principle of geologic erasure. The Earth's surface is not a static canvas, it is a dynamic, constantly changing mosaic. Civilizations are built on tectonic plates that are in constant motion. Over millions of years, the ground beneath a city can be moved thousands of kilometers, be buried under a mountain range, or be melted into the mantle. This makes the search for a lost civilization not just an archaeological problem, but a geological one. We are looking for a signal that has been stretched, broken, and scattered across a planet that has repeatedly rearranged its own furniture. But the story of Pangea also offers a glimmer of hope. The fact that we can reconstruct the ancient supercontinent with such precision, using evidence from paleomagnetism, fossils, and geology, shows that the planet's memory, while fragmented, is not entirely gone. If we learn to read the archives of deep time with enough care, we might just find a chapter we never knew was written, so let's step back and play the skeptic. What are the strongest arguments against the existence of a pre-human industrial civilization? There are several, and they are powerful. The first and most obvious is the complete lack of direct evidence. Despite a century and a half of intensive geological and paleontological study all over the world, we have not found a single, unambiguous artifact from a non-human civilization. No tools, no buildings, no fossils of intelligent beings, nothing. The out-of-place artifacts that are sometimes cited have all been debunked as either natural formations, hoaxes, or misinterpretations. For a civilization to have existed on a global scale and left absolutely no direct physical evidence is statistically improbable. The second argument is a geological one. An industrial civilization, by its nature, engages in mining. It extracts vast quantities of resources like coal, oil, metals, and rare earth elements. These activities leave massive, long-lasting scars on the landscape. Our own mines, quarries, and oil fields will be detectable as geological anomalies for millions of years. We have mapped the Earth's crust in great detail in search of resources, and in doing so we have not found any evidence of large-scale systematic resource extraction from a pre-human era. There are no ancient, depleted coal seams or strangely empty oil reservoirs. The planet's fossil fuel and mineral resources appear to be largely untouched before the arrival of humans. Third, there is the biological argument. The evolution of intelligence of the kind required to build a technological civilization is thought to be an extremely rare event. It requires a specific combination of biological traits, large brains, manipulative appendages like hands, social structures, and language. On Earth, this combination has only appeared once in 4-5 billion years in our own lineage. While other species are intelligent, none have developed the capacity for cumulative technological culture. For this to have happened twice in 2 separate lineages would be an extraordinary coincidence. Furthermore, if such a species existed, where are its descendants or its cousins? Evolution tends to produce radiating families of related species. We see this with hominins, where multiple species coexisted for millions of years. If a reptilian or insectoid civilization had existed, we would expect to find other, related intelligent or semi-intelligent species in the fossil record. We find none. Finally, there is the argument from energy. An industrial civilization consumes vast amounts of easily accessible energy, primarily fossil fuels. These fuels, coal, oil, and natural gas, are the product of hundreds of millions of years of accumulated biological material. They are a one-time inheritance from the planet. Our civilization is rapidly consuming this inheritance. If a previous civilization had done the same, they would have used up a significant portion of the easily accessible fossil fuels. This would have made it much more difficult, if not impossible, for a second industrial civilization, ours, to arise later. The fact that we found a planet with abundant, easily tapped fossil fuel reserves is, in itself, an argument that no one has been here to burn them before. These arguments, taken together, form a strong case for human uniqueness. They suggest that while the idea of a lost civilization is intriguing, the evidence from geology, biology, and chemistry points firmly in the other direction. The process of scientific discovery is often portrayed as a linear march toward truth, with each new finding building neatly on the last. But the reality is far messier. It's a process of stumbling through a dimly lit room, bumping into furniture, and slowly piecing together a map of the space. Our search for the past is limited by the tools we have, the questions we think to ask, and the assumptions that shape our interpretations. We are detectives arriving at a crime scene millions of years after the fact, with most of the evidence degraded and the witnesses long gone. Our primary tool is the geological record, but, as we've seen, it's a deeply biased narrator. It preserves the hard and the durable, the widespread and the catastrophic. It forgets the soft, the local, and the gradual. This is survivorship bias on a planetary scale, We only see what survived the great filter of deep time. This means that a civilization that built with biodegradable materials, used sustainable energy, or lived in a geologically unstable region would be almost invisible to us. Our methods are also limited. We can date a rock layer, but often only with a margin of error of tens or hundreds of thousands of years. This makes it difficult to resolve the speed of past events. A climate change that seems instantaneous in a 100-million-year-old rock might have taken millennia to unfold. We can analyze the chemistry of a sediment sample, but we are limited to the elements and compounds we know how to look for. If a past civilization used a form of technology based on materials or energy sources we don't understand, we wouldn't recognize its traces even if we were holding them in our hands. Then there is the problem of intellectual bias. Science operates with paradigms, shared sets of assumptions and theories that guide research. These paradigms are powerful and useful, but they can also create blind spots. The current paradigm in geology and paleontology does not include the possibility of a pre-human civilization. Therefore, when an anomaly is found, the default assumption is that it has a natural cause. This is not a conspiracy, it is a sensible application of Occam's razor. But it does mean that the evidence for a lost civilization would have to be overwhelming and unambiguous to break through the existing paradigm. We are pattern-seeking animals. We see faces in the clouds and canals on Mars. It is all too easy to project our own intelligence and intentions onto the natural world. A true scientific search for a lost civilization requires a deep skepticism, a constant questioning of our own interpretations. Is that a grid pattern, or is it just intersecting geological faults? Is that a chemical spike from industry or from a previously unknown type of hydrothermal vent? Every potential signal must be rigorously tested against every known natural explanation before we can even begin to consider an artificial one. This detective work is the essence of the scientific method. It is a slow, careful process of elimination. And for the question of a lost civilization, we are still at the very beginning of that process. We have not yet defined all the potential signals, developed all the necessary detection tools, or fully accounted for all our own biases. We are still learning how to ask the right questions. The room is still dark, and we are just beginning to feel our way around. So let's bring this vast, abstract question back to where we started. Here and now, in this room, inside your body. You are a system of incredible complexity, a walking, breathing ecosystem of trillions of cells, all cooperating to create the experience of being you. Your body regulates its own temperature, repairs its own tissues, and processes information from the world around you. In many ways, you are a microcosm of the planet itself, a self-regulating system that maintains a delicate balance in a constantly changing environment. The atoms that make up your body were forged in the hearts of stars billions of years ago. They have been part of mountains, oceans, dinosaurs, and ancient forests. You are literally made of stardust and recycled planet. The water in your cells has been flowing through the Earth's hydrological cycle for eons. The oxygen you breathe is a gift from countless generations of plants and algae. You are not on the Earth. You are of the Earth. This embodied perspective changes how we think about our place in the system. We are not outside observers trying to understand a separate object. We are the system trying to understand itself. Our consciousness, our intelligence, our curiosity, these are not alien intrusions into a natural world. They are emergent properties of that world, a way for the universe to look back and wonder at its own existence. This doesn't mean we have a prescribed role or purpose, but it does mean we have agency. We are not just passive products of the system, we are active participants. Our actions have consequences that ripple through the entire planetary web. The choices we make about energy, consumption, and technology are not just economic or political choices. They are geological choices. We are leaving a layer in the rock, a chemical signature that will be readable for millions of years. This brings a sense of responsibility, but also a sense of connection. The search for a lost civilization is not just a search for others, it's a search for a deeper understanding of ourselves. What does it mean to be an intelligent technological species on a finite planet? Is it possible to build a civilization that lasts, one that integrates with the planet's systems rather than overwhelming them? Or are all civilizations by their nature brief, brilliant flashes that inevitably burn themselves out? We don't have the answers. But by asking the questions, by looking into the deep past for echoes of other possibilities, we can perhaps gain the wisdom we need to shape our own future. The Earth will continue its slow, patient cycles long after we are gone. The archives will keep recording. The only question is what story our layer will tell. Let's consider the flow of energy. Any civilization, particularly an industrial one, requires a massive amount of energy to sustain its complexity. That energy has to come from somewhere, and its use inevitably leaves byproducts. The story of human civilization is, in many ways, a story of escalating energy consumption, from the burning of wood to the harnessing of fossil fuels and nuclear power. If a prior civilization existed, it would have faced the same fundamental challenge. Where did it get its energy? And what traces did that energy leave behind? If they used fossil fuels, as we do, the signature would be a release of carbon into the atmosphere, as we've discussed. But what if they used other sources? A civilization that mastered solar power on a global scale might have left a different kind of trace. Perhaps vast arrays of solar collectors would have altered the planet's albedo, its reflectivity, in a measurable way. The production of those collectors would have required mining and refining materials like silicon, leaving behind industrial waste products. A civilization that developed advanced geothermal energy would have had to drill deep into the Earth's crust, potentially altering local geology and causing seismic activity. The waste heat from such operations could have warmed rivers or coastal waters, leaving a signature in the fossil record of local ecosystems. And then there is the possibility of nuclear energy. A civilization that used nuclear fission would have produced long-lived radioactive isotopes as waste. If this waste was not securely stored, it could have been dispersed into the environment, leaving behind a clear and unambiguous techno-signature. The discovery of a 1.7 billion-year-old natural nuclear fission reactor in Oklo, Gabon, shows that such processes can occur in nature. But an artificial reactor would likely have a different isotopic fingerprint, a different geometry, and would be found in a geological context that is not conducive to natural reactor formation. The challenge is that for any of these signals to be detectable today, the energy use would have to have been on a planetary scale. A few solar panels or a single nuclear reactor would not leave a lasting global trace. The civilization would have had to transform the planet's energy budget. This brings us to a concept known as the Kardashev scale, a way of measuring a civilization's technological advancement based on the amount of energy it can use. A type swarming civilization can harness all the energy available on its home planet. A Type 2 can harness the full energy of its star, and a Type 3 can harness the energy of its entire galaxy. Human civilization is not yet a Type 1, but we are moving in that direction. If a past civilization on Earth had reached Type 1 status, its impact would be undeniable. It would have fundamentally altered the planet's climate and geology. Its energy use would be visible across deep time. The absence of such a dramatic, planet-altering signal in the geological record is, for some, the strongest evidence that such a civilization never existed. However, this assumes that all advanced civilizations follow a path of ever-increasing energy consumption. What if a civilization chose a different path? What if it developed technologies that were incredibly efficient or drew energy from sources that leave no trace, like zero-point energy or vacuum fluctuations, though these are highly speculative? Or what if a civilization, upon reaching a certain level of technological maturity, made a conscious decision to limit its growth and energy use, choosing sustainability over expansion? Such a quiet civilization might reach a high level of complexity without leaving a loud geological footprint. Its signals would be subtle, perhaps even undetectable. They might have mastered biology instead of physics, creating a civilization that was integrated with the biosphere rather than imposed upon it. Their legacy would be written in the language of life, not in the language of rock and radiation. This is where the limits of our own imagination become a factor. We tend to project our own technological path onto any hypothetical civilization. We look for signs of fire, metal, and machines because that is the path we know. But intelligence is not a monolith. There may be other ways to be complex, other ways to be civilized. And if such a civilization existed, its ghosts might be all around us, not in the ground, but in the patterns of the living world. When archaeology runs out of artifacts and geology runs out of layers, what's left are stories. Not scientific records, not measurements, but myths. Oral traditions passed down through generations, sometimes across entire civilizations. Most are changed in the telling. Details shift, meanings blur, symbols layer over each other, but myths persist. They survive even when buildings fall and languages die. And while they're rarely taken as literal history, there's a growing understanding that some of them may hold fragments of real events, coded, distorted, but not entirely imagined. This idea isn't new. Cultures around the world have myths about floods, fire, stars falling from the sky, or land that once was but is no more. They describe golden ages that ended suddenly, lost knowledge, sudden darkness, strange visitors, islands swallowed by the sea. Taken separately, each story sounds like symbolic fiction. Taken together, they begin to form patterns. One of the most persistent themes is the flood. It appears in Sumerian, Babylonian, Greek, Hindu, Norse, and biblical traditions, among many others. The details vary, but the core is consistent. A vast deluge wipes out a previous world. It's tempting to see this as simple metaphor. But there's also geological evidence of dramatic sea level rise, especially at the end of the last ice age. Glaciers melted, seas rose by over 100 meters, and entire landscapes were drowned. People living near those coasts would have seen their world vanish, and their descendants may have told stories about it. Other myths speak of lost lands: Atlantis, Mu, Lemuria. These places are often described as advanced, beautiful, and doomed. Most of these stories are viewed today as fiction, but even fiction can preserve echoes. The memory of a submerged land might be real, even if the details of its civilization are not. Then there are stories of knowledge lost. Many traditions speak of a time when people knew more, when ancient wisdom was common. These ideas don't prove anything, but they raise a question. How do cultures come to believe they used to know more than they do now? It's important to be clear. None of this proves that an advanced, non-human civilization existed. Most of these myths can be readily explained as memories of more recent human experiences, the end of the Ice Age, volcanic eruptions, tsunamis. But they do show that human culture has a long memory and a fascination with the idea of worlds before our own. If a truly ancient civilization had existed and somehow interacted with our earliest human ancestors, it is conceivable that a distorted, mythologized memory of that encounter could have been passed down through generations. It would not be a historical account, but a story, a dream, a whisper of a time when we were not alone. It's a fragile thread of evidence, perhaps the most fragile of all. But in a search this deep and dark, even whispers are worth listening to. As we draw these threads together, the erasure by time, the potential for chemical signals, the limitations of our tools, and the echoes in our stories, we can begin to frame a more holistic picture. The question is no longer a simple yes or no. It has become a question of probabilities, thresholds, and the nature of intelligence itself. We are moving toward a synthesis, a way of holding all these pieces at once without demanding a single, simple answer. The next step is to perform a kind of turn, to reframe the question itself. Instead of asking whether a civilization existed, let's ask a slightly different question. What kind of civilization could exist and leave no trace? This reframing shifts the focus from a search for evidence to an exploration of possibilities. It forces us to think outside our own technological and cultural box. We have already considered a light-touch civilization, one that built with biodegradable materials and used sustainable energy. Such a society would be almost invisible to geology. But let's push the idea further. Could there be forms of intelligence that are not technological at all? The philosopher Ludwig Wittgenstein famously said, "If a lion could speak, we could not understand him." This is because a lion's world, its concepts, its values, are so fundamentally different from our own that a shared language would be meaningless. The same might be true for a non-human intelligence. What if a species developed a profound intelligence that was entirely internal or social? Imagine a species of cetaceans that developed a complex language of song, a rich oral history, and a deep philosophical understanding of their oceanic world, but never developed manipulative appendages to build tools. They would be a civilization of mind, not of matter. They would leave no artifacts, no ruins, no chemical signatures. Their only legacy would be in the patterns of their songs echoing through the water, and in the structure of their genes. After their extinction, there would be no way for us to know they had ever been more than just another species of whale, or consider a collective intelligence like that of a fungal network or a social insect colony. A vast mycelial network can process information, share resources, and respond to its environment as a unified whole. It has memory. It makes decisions. Is it conscious? Probably not in the way we are, but could such a system develop a form of intelligence over millions of years? If it did, what would its civilization look like? It would not be a city of towers, but a living network of roots and filaments, a planetary brain woven into the soil. Its thoughts would be chemical signals. Its actions would be the slow growth and decay of ecosystems. Such a civilization would not be separate from nature. It would be an expression of it, and its traces would be indistinguishable from the natural world itself. We would be living inside its ruins without ever knowing it. These are speculative possibilities, of course, but they serve an important purpose. They remind us that our definition of civilization is a projection of our own experience. We are a species that thinks with our hands. We build, we manipulate, we transform matter. So we look for other civilizations that did the same. But this may be a form of cosmic chauvinism. The universe may be teeming with forms of intelligence and complexity that are utterly alien to us, forms that do not leave the kinds of fossils, physical or chemical, that we know how to look for. So let's try to weave these threads together. We have the Earth, a dynamic, self-regulating system that is exceptionally good at erasing its own history. We have the possibility of a civilization, which we have defined as a species that harnesses energy to a degree that it alters planetary systems. We have a set of potential signals, chemical, geological, and biological, that such a civilization might leave behind. And we have the profound challenge of detecting and recognizing these signals against the noisy background of natural processes. The case for a pre-human civilization is entirely circumstantial. There is no direct evidence. The case rests on a series of what-ifs. What if that unexplained climate event was not natural? What if that strange chemical layer is not just a geological oddity? What if the evolution of life was nudged by an unseen hand? The case against is much more direct. The absence of evidence, the geological unlikeliness of large-scale artifacts surviving, the biological rarity of human-like intelligence, the untouched state of the planet's fossil fuel reserves. In a scientific court of law, the verdict would be clear: not guilty. There is insufficient evidence to support the claim, but we are not in a court of law. We are in a space of quiet curiosity. And in this space we can hold the question open without needing to render a verdict. We can acknowledge the strength of the skeptical arguments while still appreciating the humbling power of the thought experiment. The true value of the Silurian hypothesis is not that it might be right, but that it forces us to see our own civilization in a new light. It makes us see our cities, our machines, and our pollution not as the peak of history, but as a thin layer of sediment in the making. It makes us realize that our legacy will not be our monuments or our stories, but the chemical scar we leave in the rock. And yet there is a tension here. We have described a planet that erases almost everything, and a civilization whose traces would be vanishingly faint. But we have also described a planet that is deeply ordered, with systems that seem almost too well suited for life. The Gaian feedbacks, the stabilizing presence of the moon, the unique properties of water, the mathematical elegance of biological forms. These things do not feel random. They feel like part of a coherent system. Could it be that we are looking for the wrong kind of signal? We have been searching for the traces of a civilization that acted upon the Earth, one that left scars and waste. But what if a truly advanced civilization would not leave a scar at all? What if its legacy was the opposite, a deeper level of order, a more resilient balance, a more complex harmony? Perhaps the greatest techno-signature is not a disruption in the system, but the system itself. This is a radical and unprovable idea. It moves from science into the realm of philosophy, but it is the logical extension of our inquiry. If a civilization could master geology, climate, and biology, it would not be fighting against the planet's systems. It would be indistinguishable from them. Its engineering would look like a rainforest. Its computation would look like a genome. Its energy network would look like a mycelial web. This brings us to a place of profound uncertainty. We are faced with two possibilities, both of which are humbling. The first is that we are alone in time, the first and only technological species to arise on this planet. Our future is entirely in our own hands, and the silence of the past is a warning of how easily a species can fail to emerge at all. The second possibility is that we are not the first, that others came before us and either vanished without a trace or became so integrated with the planet that we can no longer see the join. In this case, the silence of the past is not an absence, but a presence we don't yet know how to perceive. We may be walking through the ruins of a garden, mistaking it for a wilderness. Let's return to the Carboniferous period, 300 million years ago, but with this new perspective. In our first walkthrough, we imagined finding a layer of pollution and collapse. Now let's imagine a different kind of signal. Suppose we find a period in the Carboniferous that was unusually stable. For several million years, the climate barely fluctuated, despite known orbital cycles that should have caused ice ages. The biodiversity in the fossil record increased, but without the usual boom and bust cycles of extinction. The coal seams from this period are unusually pure, suggesting a highly efficient process of carbon burial. What would we make of this? Geologists might call it a period of climatic optimum, a happy accident. But a planetary archaeologist might see something else. They might see the signs of a mature civilization managing its planet. They might hypothesize that this civilization had mastered carbon sequestration, perhaps through biologically engineered forests, that it had stabilized the climate by subtly managing the planet's albedo or ocean chemistry, that it had fostered biodiversity as a way of increasing the resilience of the biosphere. The evidence would not be a scar, but a period of unusual health, a moment when the planet's vital signs were a little too steady, a little too good to be true. This would be a much harder case to make. Proving a negative, the absence of expected chaos, is scientifically difficult, but it is a possibility worth holding in mind. The ghost in the machine might not be a saboteur, it might be the machine's designer. And its greatest achievement might be that the machine runs so smoothly we no longer notice it is a machine at all. This entire exploration of deep time, lost worlds, and planetary memory can feel distant and abstract, but it has a very personal and practical application. It teaches us how to pay attention. We are surrounded by systems, natural and artificial, that are constantly giving us feedback. But we are often too busy, too distracted, or too focused on the immediate to notice the larger patterns. Learning to think like a geologist or a systems biologist is a way of training our attention. It's about learning to see the connections between things, to recognize the slow, cumulative effects of small actions, and to appreciate the deep history that is embedded in everything around us. You don't need a rock hammer or a mass spectrometer to do this. You can start right where you are. Pay attention to the weather, not just whether it is sunny or rainy, but the patterns of the clouds, the direction of the wind, the feel of the air. These are the signs of a vast atmospheric system in motion. Pay attention to the soil in your garden or a nearby park. Notice its color, its texture, the kinds of plants that grow in it. You are looking at the product of millennia of geology and biology, a living system that connects the rock beneath to the life above. Pay attention to the cycles of your own body, the rhythms of sleep and waking, hunger and fullness. You are a biological clock, tuned by evolution to the rotation of the planet. These are not small things, they are the points of contact between our individual lives and the vast, interconnected systems of the Earth. By noticing them, by taking the time to wonder at their complexity, we are practicing a form of quiet engagement. We are reminding ourselves that we are not just living on the planet, we are living in it. This practice does not require us to solve the mystery of lost civilizations, but it does equip us with the one tool that would be necessary to do so, a mind that is open to seeing the world as more than just a collection of objects, but as a web of relationships, a story written in a language we are all capable of learning to read. So where does this leave us? What can we say about the future of this question? The search for techno signatures in the geological record is a brand new field of science. The Silurian hypothesis paper was published in 2018. We are at the very beginning of learning how to look for these kinds of traces. In the coming years, we can expect this field to develop. Scientists will refine their models of what an industrial civilization's footprint would look like. They will develop new analytical techniques for detecting trace chemicals in ancient rocks, and they will begin to systematically re-examine existing geological data with this new question in mind. It's possible that we will find nothing, that the skeptical arguments will hold, and the silence of the past will remain unbroken. It is also possible that we will find anomalies that we cannot explain, signals that are suggestive but not conclusive, that deepen the mystery without resolving it. And it is even possible, however remote it may seem, that we will find a clear and unambiguous signal, a chemical fingerprint in a deep layer of rock that tells us, beyond a reasonable doubt, that we were not the first. If that day ever comes, it will be one of the most profound discoveries in human history. It will reshape our understanding of ourselves, our planet, and our place in the universe. It will be a moment of connection across the abyss of deep time, a message in a bottle that has finally washed ashore. Whatever the outcome, the very act of searching has value. It pushes the boundaries of our science and our imagination. It forces us to confront the vastness of time and the fragility of our own existence. And it cultivates a sense of humility, a recognition that we are a small part of a much larger and older story. The Earth is a story that is still being written, and we are one of its authors. But we may not be the first, and the traces of those who came before may be all around us, not in grand monuments, but in the subtle language of the planet itself. They may be in the carbon in the air, the salt in the sea, the rock beneath our feet, and the code within our cells. We have only to learn how to listen. The story of our planet is one of cycles. Cycles of heat and ice, of life and extinction, of continents gathering and breaking apart. And perhaps, just perhaps, it is also a story of cycles of intelligence, of civilizations rising, falling, and being forgotten, leaving behind only the faintest of whispers in the deep archive of the Earth. Humility isn't something science demands, but it is something the universe tends to enforce. Every time we've assumed we were at the center of things, we've been moved outward, first from the Earth, then from the Sun, then from any special place in the galaxy. And now, when we look at the deep past of our own planet and ask if we were the first to reach this level of awareness, we face another kind of decentralization. One that doesn't say we weren't first, but gently reminds us we might not know either way. This is the humbling possibility that intelligence is not unique, that it can arise more than once on the same planet, and that it can vanish so thoroughly we wouldn't even notice. Not because it didn't leave traces, but because we've already explained those traces away or never saw them in the first place. We tend to think that if something important happened, it would be obvious. But that belief assumes permanence is normal. It isn't. The vast majority of human history has been lost even from the last 10,000 years. Entire cultures left no written records. Entire cities left no visible ruins. How much more could be missing from 10 million years ago or 100? The geological record isn't a book. It's a puzzle missing most of its pieces with no picture on the box. And we only notice pieces that contrast sharply with the rest. Something black in a white layer, something jagged in a smooth one. This is why the idea of a pre-human civilization is so difficult to explore, not because it's absurd, but because it exists in the exact space where evidence is weakest and interpretation is softest. It requires science to make room for doubt without abandoning rigor. Most scientists don't resist the idea out of arrogance. They resist it out of training. Extraordinary claims require extraordinary evidence, and so far there isn't any. But absence of evidence isn't evidence of absence. And sometimes the scale of time is so large that silence becomes the dominant feature, not because nothing happened, but because the Earth is good at forgetting. And that's where humility returns, not as a surrender, but as a way of staying honest. We don't know if we're the first. We may never know, and if we aren't, we may never find the proof. And if we do find it, we may not recognize it for what it is. The question of whether Earth was designed or if life is an emergent property of its systems is perhaps the ultimate framing of our inquiry. The design argument, in its classical form, suggests that the complexity and fine-tuning of the universe point to an intelligent creator. The emergence argument posits that complexity can arise naturally from simple rules and feedback loops without any need for a guiding hand. Our exploration of a lost civilization has touched on both of these ideas. A search for the ruins of a past civilization is, in a sense, a search for a kind of design, for artifacts and structures that were intentionally made. But a search for a chemical fingerprint is more like a search for an emergent property, a systemic consequence of a civilization's collective behavior. The two frames are not mutually exclusive. A civilization could be an emergent property of a planet that was itself designed. Or a universe that allows for emergence could be the ultimate form of design. What's interesting is that both perspectives, when pushed to their limits, arrive at a similar place of awe and humility. The religious believer looks at the beauty and complexity of the world and sees the hand of God. The scientist looks at the same world and sees the power of physical laws and evolutionary processes unfolding over billions of years. Both are looking at the same reality. They are just using different languages to describe the same sense of wonder. The question of a lost civilization sits at the intersection of these two languages. It is a scientific question that can be investigated with the tools of geology and chemistry, but it is also a philosophical question that touches on our deepest beliefs about meaning, purpose, and our place in the cosmos. And perhaps in the end, that is where it should remain, not as a solved problem, but as a shared question, a space where science and wonder can meet, where we can marvel at the intricate machinery of our planet and still leave room for the possibility of ghosts in that machine. This journey through deep time has brought us back to the present, to our own bodies, our own lives on the surface of this planet. The questions we have asked about the past are not just about the past, they are about us. We are the ones who wonder, we are the ones who search, and we are the ones who are now writing our own layer into the geological record. What we have learned is that we are part of a vast, ancient, and interconnected system. We are not separate from the Earth. We are a temporary expression of it. Our intelligence is not an alien force, but a product of the same evolutionary processes that created forests and fungi and fish. And our civilization is not an end point, but a phase, a planetary experiment whose outcome is not yet known. This perspective does not diminish us. It connects us. It makes us part of a story that is far grander and more mysterious than we ever imagined. It suggests that we are not just living on a rock, but inside a system that may have a memory, a rhythm, and a kind of distributed intelligence that we are only beginning to understand. To feel this connection is to feel a sense of belonging, not just to a nation or a species, but to a planet. It's a feeling of being at home in the universe, of being part of something that is both ancient and alive, and from that feeling of belonging comes a sense of responsibility. Not a burden, but a quiet, steady call to care, to act in a way that honors the complexity and the fragility of the system that sustains us, to be good ancestors, not just to future generations of humans, but to the future of the planet itself. We began with a simple, unsettling question. What if we're not the first? We have traveled through 500 million years of deep time, exploring the forces that erase history and the faint signals that might survive. We've considered the possibility of civilizations without metal, intelligences without technology, and legacies written not in stone but in chemistry and code. We have found no easy answers, no smoking guns. The silence of the past remains profound. But we have found a new way of looking at our world. We have learned to see the Earth not as a stage, but as an actor, a dynamic system that participates in the story of life. We have seen that our own civilization is a geological force, leaving a fingerprint that will outlast our grandest monuments. And we have been humbled by the scale of time and the fragility of our own moment in it. The question, in the end, is not just about who came before us. It is about what it means to be here now, on a planet that may have forgotten more stories than we will ever tell. Thank you for joining me on this slow journey through a deep question. Whether you're nodding off or just getting started thinking, I'm grateful we could share this quiet space. The world is full of mysteries, and it's a privilege to be able to wonder about them together. If you've enjoyed this exploration and want more of this kind of slow, curious science, you know what to do. A like or a subscribe is always appreciated, but your attention is the most valuable thing of all. Thank you for lending it to this small corner of the universe tonight. And so we are here at the quiet edge of the question after all the digging, all the wondering, all the long walks through layers of stone and memory. And maybe we're left not with certainty, but with stillness. And in that stillness, something gentle happens. The question softens, not because it's answered, but because it's been heard. Maybe we are the first, maybe we're not. Maybe intelligence is rare, or maybe it's shy. Maybe it blooms in hidden corners and fades before it leaves a mark. Maybe the Earth has carried more minds than we'll ever know, each flickering into awareness, shaping their time, then slipping quietly beneath the next layer. We search because it's what minds do, not just to find, but to reach through time, through space, through possibility. The same curiosity that sends probes to other planets sends thoughts into the past, asking who else might have stood where we now stand, looking up, wondering, listening. And you right now, wherever you are, whenever it is, you're part of that, part of the long thread that ties questions to silence and silence to story. Even just by listening, by following this trail of thoughts through the dark, you're participating in something deeply human, or maybe not just human, maybe conscious, maybe universal. Because sleep too is a kind of deep time, a letting go of the surface, a sinking into layers. And when you drift off tonight, you'll be entering a space not so different from the one we've explored, quiet, vast, unlit by certainty. And maybe, just maybe, somewhere in that stillness, the minds that came before, if they came at all, will meet yours in passing, not with answers, but with company. So rest now, not because the questions are over, but because you've carried them far enough for one night. The past will wait. The earth will keep spinning, and whatever came before, whatever comes next, you're here now. Look up from where you are, the ceiling, the sky, the darkness above your head. That space is not empty. It is filled with the air that connects you to the entire planet. The oxygen in your next breath may have been released by a plankton in the Southern Ocean or a tree in the Siberian taiga. The carbon dioxide you exhale will join this global flow, perhaps to be taken up by a plant in your own neighborhood. You are part of the Earth's breath. Now feel the ground beneath you, the floor, the foundation, the deep rock below. You are resting on a tectonic plate that is drifting at the speed your fingernails grow. A few million years ago, the ground you are on was somewhere else entirely, and a few million years from now, it will have moved again. You are a passenger on a slow, geological journey. The materials around you, the wood, the metal, the plastic, all came from the Earth's crust, products of planetary processes that unfolded over eons. The energy that lights your room and powers your device was likely released from fossil fuels, the stored sunlight of ancient forests. You are living inside the planet's memory, and your own body, a collection of water, carbon, and minerals, is a temporary arrangement of the Earth's own substance. You are not a visitor here. You are a feature of the landscape, and your thoughts, your questions, your wonder, these are not separate from the world. They are a way the world comes to know itself. So as you drift into sleep, remember that you are not just in your room. You are in a system, you are in a story, and you are not the first to wonder where it began or where it is going. You are just the latest voice in a conversation that may be as old as the planet itself. Sleep well, time traveler.